So we arrived to our second example on derivatives as a function. This is going to be an application. In this example, they are giving us a position function. So the position of an object after t hours. They want us to find if the object is moving right or left at time t equals 10 hours, and if the object stops moving at some point. We can answer this by just looking at the graph. If we recall that this is a position function, then the x-axis is time, which is given in hours, and the y-axis is the position, which is given in a distance. Now, what does the tangent line mean in this example? At this point, the tangent line would be right here. So in this type of applications, we set up right and left to be either positive or negative. It's usually used positive when the object is moving to the right and negative when it is moving to the left. The derivative is just the rate at which the position is changing according to time. So if the tangent line has a positive slope, the object is moving to the right. And that is what's happening at this point. As we go on in time, the tangent line gets less and less steep, as you can see. It's less and less steep. It's almost horizontal, but it's not. It still have a little steepness. So we could answer the questions A and B without even doing the algebra. Look, at time t, the object has a positive slope, very small but positive. That means that it's moving to the right. And for the second question, as you can see, over time, this function continues growing and growing, very slowly, but growing and growing. That means that the object is not stopping at any point. But let's do the algebra. So for this, to do it algebraically, we definitely need to find the derivative of g at t. This is what we're looking for. And we will do that by definition. So the derivative of g at t is the limit as h approaches 0 of g of t plus h minus g of t all over h. So let's replace t plus h here for t and here for t in the function. So we get the limit as h approaches 0 of g of t plus h is going to be then t plus h on the top, and then t plus h plus 1 in the denominator, minus, and we just write g of t, t over t plus 1, all over h. Do the LCD, and at the end what we have to do is take the first term, plus h plus 1, and multiply and divide by t plus 1 over t plus 1 minus t over t plus 1, and multiply by t plus h plus 1 over t plus h plus 1, all over h. And so we get the limit as h approaches 0, and then in the numerator we get t plus h times t plus 1 minus t times t plus h plus 1 all over t plus h plus 1 times t plus 1 all over h. And remember, the h has a 1, and we again have a complex fraction. So we keep the numerator, which I'm going to distribute at the same time. So this is t times t, t squared, plus t plus th plus h minus t squared minus th minus t, all over t plus h plus 1 times t plus 1. So we keep the numerator and multiply by the reciprocal of the denominator. So that's the limit as a approaches 0. And now the t squares cancel out, the t's cancel out, t times h cancel out. We only have h in the top, and in the denominator the same thing, times t plus 1 times h. And now the h is canceled out, and we get the limit as h approaches 0 of 1 over t plus h plus 1 times t plus 1. And when we take the limit and h approaches 0, this is 1 over t plus 1 times t plus 1. So this tells us that the derivative of g at t is 1 over t plus 1 squared. Now we answer the questions. At all times, remember that the derivative in this example is the velocity. So to answer question A, we would like to find the velocity at time 10. So we plug in 10 in the derivative, which gives us 1 over 11, which is 1 over 121. And because it's positive, the object is moving right. To answer the second question, you say, okay, is this ever going to stop moving? Well, an object would stop moving if the velocity is 0. If we set up the velocity to be 0, then g prime of t would be 0. That means 1 over t plus 1 squared would be 0. And, well, ask yourselves, when is that 0? Recall that any fraction is 0 if and only if the numerator is 0, because the denominator can never be 0 or it would not be defined. In our example, that object never stops moving. So now you see how the graph matches the algebra? Algebraically, we can say that this equation doesn't have solution. Hence, the object never stops. Thank you.